So after the last couple of videos, you kind of get a sense of what a log graph looks like. My next obvious step is to then apply some transformations to those log graphs. So 6.3 is on transformations of logarithms. All right, let's begin with the warm-up. Number 1, why is it not possible to determine the following logarithms? In fact, why don't you grab your calculator and try to calculate this, log of 0. See what you get. Does it equal to an error? Okay, try the next one, log of -3 or log of -10. Do you get the same thing? Well, none of these are possible because this x value, this guy right here, cannot be a 0 and it can't be anything less than a 0, so a negative number. I'm going to explain that in two ways, algebraically and then graphically. Okay, so algebraically, I'm trying to figure out what this equals to. That should be an equal sign. Okay, so the base, which is an invisible 10, to the power of what number gives you a 0? 10 to the power of what gives you 0? Maybe 0. 10 to the power of 0 gives you, no, it's 1. Okay, so that doesn't work. 10 to the power of a negative number? No, then that would be a fraction. Or a decimal, I guess. Okay, and 10 to the power of maybe a positive number would be much bigger than 0. So you see, there is no number here that exists where 10 to the power of it will give you a 0. And that's the same for these guys. 10 to the power of nothing will give you a negative number. Okay, so algebraically, it really just doesn't make sense. Now, if I show you graphically, remember that this red graph is a log graph. Here's your x right here. And then notice your x's, your domain for your red graph. They're all bigger than 0. Okay, now it never does reach 0 because you have that vertical asymptote right here. So algebraically, it also doesn't make sense to have a 0 or a negative as your x value. All right, so number 2, how are the graphs of the following functions related? So f at x looks like it's an exponential graph, and then g of x looks like a logarithmic graph. So that's like the two graphs that we just saw in blue and red. These guys are inverses of each other. So you see, this guy is the exponential, and then this one is that logarithmic graph. Okay, now what I've done here is I've just given you some extra coordinates that you can use before we start to transform things. Okay, so I'm just going to review that really quickly. This guy is a major point on any exponential graph. It is always 0, 1. So we know that on a log graph, we're going to always have the switch of that, which is 1, 0. Okay, so this is a major point on the log graph. Another major point will be from this point right here. Okay, so this point really depends on whatever your base was. So I believe in this graph, it looks like the base was probably 2. So 2 to the power of your x value, looks like your x value probably was 1. 2 to the power of 1 is 2, and that's why you get a dot right here. That means that this point is always 1 for your x value, your exponent, and that's going to give you an answer of the exact same base that you were dealing with. Okay, so if I switch these guys around, I get the inverted point, and that is another major point on your logarithmic graph. These 2 points are going to be very important when I start to do the mapping notation for any transformations. Okay, so here's some extra information that I went over in a previous video. Just know that any of the exponential information is kind of like inverted or reversed in the logarithmic one. So remember that horizontal asymptote that was in the blue graph, well, now it's a vertical asymptote. All right, then these guys also switch to none. So if you didn't have a vertical asymptote before, you will have one now because now you don't have a horizontal asymptote. All right, the domain and range, they kind of switch too, and your x and your y intercept. All right, so that's just a really quick review, and any of the transformations that we've seen before on any other graph are exactly the same. Your A is still going to be your vertical stretch or compression, that's your horizontal stretch or compression, and then you have your up or down, your left or your right. Okay, now instead of your f for function, we're going to put in log to indicate that it's a logarithmic function. All right, so nothing has changed. It's all basically the same. Now what we're going to do is, like I said, we need some major points that we can use for the mapping notation. So remember, those major red points that I had indicated before was 1 and 0. That was your x-intercept, okay, and b and 1. So this is b represents whatever your base number is. So whatever this is, that's going to be. You're going to then apply your transformations. Okay, so here are your original red numbers. We'll just pretend that those are red. Okay, right there. And then we're going to multiply your A's, we're going to add your C's, and we got to do the opposite of your horizontal transformations. So instead of K, it's going to be 1 over K. Instead of a minus, it's going to be plus D. All right. Now, one other thing. In the, let's see, it was the red graph, you had a vertical asymptote, all right? And it's going to shift left and right, so horizontally, depending on whatever your D is. So if this is a left or right, your vertical asymptote also shifts. And I'll show you how that works. Okay. All right, let's start off with our first example. We have an equation right here. Sometimes they do write in 10, but remember, if it's invisible, we automatically know it's a 10. So this is a common logarithm. Okay, and what we're going to do is we're going to just describe the transformations. Okay, so describing the transformations. There is a vertical stretch by a factor of 2. You see it goes to the right 3, and then it goes up 4. That's simple stuff. Now, on a separate slide, I'm just going to show you the next couple questions. So B is asking you to graph it. Then you're going to state the vertical asymptote. In fact, we actually need to do this before we graph. And then we'll talk about the domain and range. Okay, so I'll do all three of those things on the same slide. Okay, so here is the original equation. These are our original points. Okay, so remember, 1, 0 is always a point on any log graph. And then also the 10 comes from your base. So whatever this number is, that's going to be the first one. And it's always a 1 over here. Now let's apply the transformations to these original coordinates. Okay, so your vertical stretch by a factor of 2, your vertical translation by a factor of 4, I got those right there in red. And then, remember, we do the opposite, so it's not going to go to the left, it's actually going to go to the right. We need to add 3, all right? Then you're going to calculate your new numbers, and there you go. These two dots are on your graph, and you're just going to graph them. So you need a graph, first of all. And you know what actually helps a little bit is your asymptote. So why don't we figure out our asymptote? Remember what I said, it's actually going to be related to this number right here. It's going to be the opposite of this guy. So x equals positive 3 is where your asymptote is, because your asymptote was here before, but since it moved to the right, it should be at positive 3 now. Okay, so I'm just going to put that in. Now put in your two dots, your 4, 4, and your 13, 6, and you should kind of have what your graph looks like. Okay, so remember, your log graph did kind of go this way, and we kind of know it goes in this shape because we didn't have any, there were no flips or anything like that, no reflections. So this was that shape that we had before. All right, now D asks you to do your domain and range. So here we go, your domain is limited because it has to be anything bigger than 3. So I got that right there. And then your range is not. It goes on forever downwards, and this guy keeps going upwards. So your Y belongs to all real numbers. Okay, let's answer that last part. E, if 102 is a point on the base graph, state the coordinates of the transformed point on g of x. Okay, so what they're asking you is, if this was a point on your original graph, then what is the point now on your new transformed graph? Okay, so what I'm going to do is I'm just going to put this into my mapping notation, table, and then I'm going to apply the same transformations. So this should be your new point, which is going to be, whoops, let's just go back for a second, 103 and 8. So the original point, which was here on the original graph, now after all of these transformations is going to be right here. All right, so the next one, It's a little bit easier. What I'm going to do is I'm going to give you the original graph, okay, so no transformations. It's a graph with a base of 10, but I want you to apply all of these transformations to it and give me a new function. Okay, you don't have to graph it, just give me the new function. So you start off with what kind of looks like the old function. Now, I didn't write the 10 in because remember, if it's invisible, there is a 10 there. But I'm going to start to put all those transformations in. A vertical compression by a factor of a quarter means that I'm going to have a quarter right here. Okay, horizontal translation, right 5 units. Okay, so that goes in here, but it's a minus to go to the right. Vertical translation up 10 units means plus 10. And then a reflection in the y-axis. Okay, so y-axis means a horizontal translation, horizontal reflection, which means a minus right here. Okay, and that's it. All right, let's try something obviously a little bit more difficult. Do you see this guy right in here? Well, it looks like to the right of 6, but it's not. You're going to have to factor out that -3 so that you really see what that horizontal translation is. It's going to the left 2. Okay, so this one's a little bit trickier because it just requires you to factor, but we know that trick already. Okay, so let's start sketching this. We're going to need all of that information, all right, and we'll do the domain and range as well. Okay, so first of all, here are our original coordinates. Remember, 1 and 0 is always those numbers, and then you take the base, which is 2, and then this one's always a 1 that goes with it. Okay, apply your transformations, so your 2 and your 4 are as is, but your 3 is going to be 1/3, still negative, okay, just the 1/3 is going to be opposite. And then you also have your 2, which is now a -2. Okay, so calculate your new numbers. And then I think the next part would probably be, you should probably find the asymptote. And remember, you look up here for the asymptote. Okay, so opposite of this guy, which is -2, is going to be your asymptote. That makes sense because your vertical asymptote moved to the left 2. Okay, so it was here before, and now it's going to be here. Graph your points, so -2.3 and 4, and -2.76. So those are my 2 points approximately, and I'm just going to graph the rest. So since the original log graph should have been over here, it should make sense that it's flipped onto this side because there was a horizontal reflection. All right, now really quickly, your domain and range. Okay, so domain, it looks like your graph is anything less than -2. And then your range is still going on forever in both directions. So y belongs to all real numbers. Okay, so I mean, there's nothing really new in terms of transformations in general. The only new thing is really understanding what these original points were so that we can actually map the new points onto the graph.